Hello all. Uh, this is Unit 3, uh, Labs in Electricity, Magnetism and Light. Today we're going to cover Ohm's law and Kirchhoff's laws. These both of these laws, states the relationship between current, voltage, and resistance. In Ohm's law, you'll see, how current uh, depends on the voltage and the resistance. Um, Kirchhoff's laws states the similar things, but we use Kirchhoff's laws to solve more complex multi-loop circuits. To define Ohm's law, we need to understand what current, resistance, and voltage is. We have covered all this in class by now. Um, the voltage, first, it is the potential difference or just the electric potential. um, it is defined as the electric potential energy per unit charge. This is our battery here that provides that potential difference or the voltage. And once a wire is connected around a battery or of any potential source, uh, the the free electrons in the cell and in the wire, a conducting metal wire, uh, sees this potential difference of the battery, and the electrons move along the wire. And now we can measure the movement of the charges in the wire, or the charge per unit time, how many charges pass any cross-sectional area in given time. That's the measure of the current. And next is the resistance. It's the physical property of any conductor or the resistor itself uh, that resist the flow of the charges. And as a result, result of that resistance of any wire or the resistor, like the tungsten filament in a bulb, the electrons that are moving have kinetic energy, and that kinetic energy is lost, you know, in the resistor, and that lost energy is converted into heat and light. um, but these electrons are constantly under the potential difference of the battery here. Um, this battery provides constant potential, and every electron in the wire are under that potential difference. So even they lose the kinetic energy at the light bulb, they continue to go around the loop. And so those are voltage, current, and resistance. Then George Simon Ohm, experimentally verified that current in the wire is proportional to the voltage, and that proportionality constant is replaced by R, the resistance of the wire, meaning how much current can flow through the wire um, depends on the voltage and the resistance. And you put these together into a very popular formula, V equals to IR. This is the Ohm's law. And again, current depends on the voltage and resistance. You can also understand this is outside the Ohm's law, or I mean, it is related to the current or the flow of the electron. You can also understand this concept as when you have two plates here, positive and negative, there's electric field. The electric field go from positive to negative. So the electric field will move left, okay, opposite to the direction of the electron flow. So electron field goes from this along this wire all the way to the negative end. And the force exerted on the electron by the electric field is the direction of that force is opposite to the electric field. So electric field is directed left and upward, but the force on those electrons is opposite, so hence it's down and to the right. Hence the direction of electric field is along the direction of the current, which is clockwise. However, you see the direction of electron as counterclockwise in this example, and that is why the direction of electron is different than the direction of conventional current. And we can put these resistors here. This one here, we are using as one resistor. Also, it's important to note that for most of our lab examples, or even in lecture problems, when we add a high resistance resistor here, we ignore the resistance of the wire itself. Compared to these resistors here, the copper, or you usually use copper, the resistance of the copper is very low, negligible, so we ignore that. However, if we put any high resistance resistors, in series like this, we will need to calculate the equivalent resistance, and the as if what would be the net resistance of all the resistors added in series, like in this format. I go up to Rn, meaning n however many, n is an integer, goes to infinity. So R series is just sum of R1, R2, R3, and so on, however many resistors you have connected it to a potential source. That's in R connected in series. We can also have resistors connected in parallel like this here, but in this case, your equivalent resistance, like 1 over R equivalent or 1 parallel, would be the 1 over R1 plus 1 over R2 and so on. These are two combinations of resistors, in series and parallel. Any question here? Okay, no questions. Next is Kirchoff's laws. Kirchoff's, wrote these two different rules based on the electron charge conservation and energy conservation. I'll take this, multi-loop circuits to explain what Kirchhoff's laws are, and I'll show you to write equations for each of these loops and then we will learn to solve those equations to get the required values. So Kirchhoff's laws, or Kirchhoff's current law, explains that the sum of current entering a junction is equal to sum of current leaving it. What that means is, in this example, you can take any junction here, this one or that one, where all of the three currents meet. So in this junction here, the incoming currents are I1. So I1 flows from this section all the way up here to that junction. So I1 is incoming current. I2 is also incoming towards that junction. But from here until here, the current I3 leaves that junction. Hence, the I1 plus I2 is equal to I3 at that junction. And that's the Kirchhoff current law, or the junction rule. And the second one is loop rule. In any loop, so for example, this is the top loop here. This is the bottom loop. When we consider bottom loop, you can ignore this section here. and the outer loop. So the outer loop from this junction would be all the way to RD, come down here, E1, RA, RB, and back to the same point. That would complete one loop. And in outer loop case, we can ignore the middle part here. And so the loop rule states that sum of changes in the potential around any closed loop is equal to 0. So there are three loops here. You can take any, the top, bottom, or the outer one. Here the sum of changes in potential around a closed loop is 0. What that means is we'll take a test charge, like for example my pointer here. Our test charge is always positive. So let me take this test charge here along current I3 along this direction. So I'm starting at that point and going from here uh, to for this test charge we are measuring the changes of potentials of this test charge. Okay, so here the test charge goes through RD or the resistor here, and what is the potential change of this test charge as it passes through the resistor. Okay, so for this resistor and current direction I3 is to the right, so that means your current always flows from high potential to low potential. Okay, that's one key point, please do not forget that. Current flows from high potential to low potential, so that means your positive test charge here as it goes from high potential and here to low potential, the potential decreases. And what's the potential equals here? From Ohm's law, V equals to IR, and we'll write that potential change, which is negative I3 times RD. And as you go here, and we're taking the, just for example, the upper loop, and we reach to the EMF, and so in this EMF source or the voltage, the smaller one, the smaller line here is always negative, the taller one is positive. So for the positive test charge, as it goes from low potential to high potential, negative to positive, that charge gains energy, hence the potential change here is positive, and here it's negative, it drops and reaches that point. And so the sum of changes of potential of that test charge in three element, these two resistor and one battery, that sum must be is equal to 0. That's the conservation of energy as well, or an electron's energy is conserved as it makes one complete loop. Either way we can understand that. So same example. So this is the previous circuit that I showed. When you do problems, you can first replace all these numbers by a variable. That will be easier for you to write your equations. I'm replacing 8 ohms, all these resistor values by variables RD, RC, RB, and RA, and all my potentials are E1, E2, and E3. And so I'm gonna take this junction here and write the current rule or conservation of charge, and that's easy because it's the sum of incoming current is equal to sum of outgoing current. So here only one current is outgoing, which is I3, and the incoming currents are I1 and I2, hence I1 plus I2 is equal to I3. That's one equation. Okay, so here in this example, or in many of the examples that we will do, you will usually have three unknowns. Here you have all the potential sources and the resistors known. The unknowns are three currents, I1, I2, and I3. So in order to solve three unknowns, you will need at least three equations. So one comes from the junction rule, and the second we will write the loop rule for two different rules, two different loops. And so here the outer loop, I'm going to take the outer loop here. So this outer loop, I'm going to start here and take my positive test charge along the direction of current here and follow the outer line here. So Um, Here again, I'll follow this route. Once I hit the resistor, again, this is at positive end, that's at negative end. How do I know? I'm assuming that's the direction of current, I3 here. And if this is direction of current, then this must be the positive end, and that's the negative side. And positive polarity, negative polarity. And so my test charge here, as I explained earlier, the potential drops as it goes from high potential to low potential. The potential energy of the charge decreases, and hence that's and potential is from Ohm's law is equal to V is equal to IR, so that's IR. I should have written that I3 times RD, but the location doesn't matter. So and that's negative. That means the loss of potential energy. Okay, and as I'm going the outer loop, so reach that junction and follow, you know, this direction here, and when I reach here, that I go from low potential to high potential, so that's E1 positive E. So again, that's the voltage, right? And that's positive. And so what's the potential here or the voltage here for that charge? It's going from high towards low, hence the potential decreases, right? And that's I1 times RA1, which is negative. And then you reach potential source E2. You gain because you go from low to high, hence that is positive E2. And you reach RB resistor, so you go from again high towards low, the energy decreases, which is V equals to IR, but I is I1 and resistor is RB. So remember, within the same equation here, within the outer loop, there are two currents. For this section here, from this junction to this junction, it's I3 in control. And there's one element, RD, hence that has I3 component, but underneath here, there is the I1 is in control. So I1 passes through EMF1, resistor RA, EMF2, and resistor RB. So these elements will have I1 terms associated with them, I1, I1. And the bottom loop, so let's take the bottom loop and go clockwise direction. Okay, so bottom loop clockwise, so here I'm gonna go right. Okay, so as I take my positive test charge to the right, look at that resistor here. This is current goes to the left. So this is at high potential and low potential. So you see, and as my positive test charge, as I take it from low potential to high potential, it gains energy. Hence that is positive. So I2RC is positive, unlike we are negative when we go with the current from high potential to low potential in the first example. So that's positive I2RC. And now when it gets to EMF E3, remember that charge is going from high potential to low potential. When object falls from high potential to low potential, its energy decreases. So that's negative E3. Okay, and it gets to this junction. We are following the bottom loop. So from here it reaches this way going clockwise. When it reaches EMF1, now that charge is going from low to high potential, hence there's a gain in potential, hence that potential is positive. And in both of these loops, similar to before, the charge, the positive test charge loses energy here, hence those are negative, and it gains EMF or it gains potential here, and that's positive, and set that to 0. So this is how you write Kirchhoff's equations. So based on two rules. Again, since we need three equations to solve for three unknowns, here we don't have I1, I2, and I3. we needed three equations. I have one. This is the simplest of the equation, only dependent on the current. But here these are, coupled in resistance R and E. But all of the R and E values are known. Even here and here, all of these values are given here. Only unknowns in these three equations are I1 and I2 and I3. You can use the substitution method. Uh, Here, this is coupled in I1 and I3, this equation. The bottom equation is coupled in I1 and I2. So solve I1 from here, isolate I1. Okay, put everything on the right hand side, but just I1 on the left, and put that right hand side value, substitute value of I1 back in here. Then you'll have, either I1 or I2. You can isolate for I1 and I2 and substitute I1 from here and I2 from here back into equation 1 and write one equation with only one variable and solve for that variable. Again, that's the theory part. I'll let you practice that later. The answer, I believe, you can check, of course. I1, I solved for only one current, that's 0.85 ampere. And actually, that's the answer. It's looking here, but you can have multiple questions to find values of I1, I2, and I3. So once you know, this is the hard part here, writing the equations. After that, it's just your algebra skills. Please practice this at home. And I would like to move on to the simulations. I like this cartoon here. This is the essence of what Ohm's law is. It explains neatly. It's funny, but the ohm is the unit of resistance. Amp is the unit of current, ampere, and potential is the volt. Right. So this is like a battery. So battery provides the required potential difference for the electrons to move. In other words, the battery forces the electrons to go through the wire, but at the same time there is resistance in the wire that tries to stop that flow. So as usual, this manual is posted for you to review before the lab in Canvas. Here's the required theory for Ohm's law, for resistors, to get the resistors, equivalent resistance for resistors connected in series and parallel. You can follow through this theory, and here are some practice questions in your pre-lab. As usual, please type all your answers in blue. It helps to clearly differentiate between the questions and answers itself. This pre-lab is worth 15 points, so please be careful with working with these pre-lab questions. And for as an example, here's a circuit with two loops, and it asks you to write the Kirchoff's laws. Based on Kirchoff's laws, write two equations, I believe, four equations. The current equation will be very similar, but you can pick any two different junction. But most importantly, write the two voltage equation, or the loop, based on the loop rule for loop 1 and loop 2. Okay. You don't have to solve it for the pre-lab part. You can just show your equation here. And there are two parts for the simulation. Part A is Ohm's law, part B is Kirchhoff's laws. And I think Ohm's law is very simple, yet conceptual. As usual, go to your simulation site, and here you can play with two variables. Luckily, there's no third variable here. You can change the voltage and resistance of this circuit here. I'm gonna start with low voltage. Here is your voltage source, and here is a resistor here. Um, I can either decrease voltage up to 0.1 or increase as much as 9 volts, and I can also play with the resistance. Okay, there are a lot of um, you know things that are happening here as I change the voltage and resistance, and those are all pointed here in numbers 1 to 3, and you are also asked to demonstrate your understanding of the Ohm's law based on this circuit here. So again, as I explained in the theory part earlier, your current depends on the voltage and resistance, right? So here you can see the current value change as I change the voltage. So here is the minimum voltage, and I'm gonna reduce my resistance to 10 ohm only, so that's the least resistance I'm providing. So as I increase the voltage, for the lowest resistance value, current significantly increases from 10 milliamp, it goes as high as 900 milliamp. Okay, and at the same time now, if I, for the same voltage 9 volts, if I increase the resistance, what should happen to the current? It should decrease, because resistance slows down the electron flow. And so here, as R goes up, my current decreases to 9 milliamp only. And for both, at the same time now, if I decrease, so lowest voltage value and the highest resistance value, I get the lowest amount of current, and vice versa. For highest voltage and the lowest resistance, I get the maximum current. And should have a way to build this circuit. So here, uh, explain your understanding of what we just did, demonstrate your understanding here. And also there is another circuit that you can build very similar to this one here. Consider the two circuits here. The one connected to a battery, to one battery can be 9 volts, 3 volts, connected to one light bulb versus two light bulbs. Okay, here you'll have to um, write, what happens when the switches are turned on, or turn closed means the switches are turned on, and these are in the office state. Uh, you have this experience from last lab as well, how the brightness of the light bulb changes for one battery versus two battery, or when it's connected to one battery source, but now you increase the load, or you increase the bulb numbers, compare the brightness of the one bulb to the two bulbs when they are connected to the same battery source. And in the second part, there are two light bulbs. Now they are both connected to the uh, first one connected to the one battery, versus the you're doubling the batteries or the potential here, and see how that changes the brightness in the light bulb. Explain what you see, and here it asks you point wise, and so that these things stays in order. And so complete these three sections for your Ohm's law, and uh, here you can write these things based on based on your understanding, theoretical understanding. However, in the last section, build excuse me uh, build these type of circuits for this part here, um, and check your answers. Use the values obtained from the ammeter and Ohm's law to explain the differences in brightness from the two circuits. So um, here, please use this ammeter here to measure the current with your battery. Take your ammeter and you can measure the current flowing through it. Of course, you'll need a load and wire connected to it this way. Try to draw a nice looking circuits. Uh, Easier to grade. I can even cut it, bring it here, use another wire just to make it look a little nicer. And this one, measures current through the wire here, and it's 0.9 ampere. Uh, let's cut it, and what I can do is add another light bulb. The right way I need that. Here, 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 and here. Okay. So you see now, as I increase the load, is like increasing resistance, and my current has reduced versus when there was only one light bulb. So construct these as it directs here, and complete these two sections. And as usual, please capture the circuits wherever it's possible, and insert it here within your uh, report. Okay. And so the part B is the Kirchoff's law. Uh, it's the theory is what we studied earlier today. Building a circuit. Again, take your time. Include all of these uh, parameters or all of these elements carefully in your circuit. Here, this is the link. Once you're in the link, pick this lab section. Here you'll find high resistor, high resistance resistor, and as usual there are other elements like batteries and wires. As you can connect it as it asks for you in the diagram here. So here use 9 volts batteries for your E1, your EMF 1, your voltage 1, your voltage 2. There are 2 voltage source and 3 resistors. Okay, you can go in the loop suggested here and write your current direction. You can measure the current. So here, once you have uh, these elements set, you can set the values of these resistors. Just click on the resistor, and I believe those are 1000 ohm for 1, 2, 1000 and 100. So for 1 you can increase the resistance value to 1000. So this one has 1000 ohms. Be careful with this. Again, um, you won't see the in this section, intro section, this resistor can only go up to about 10 ohm, I guess, I believe, and this one you can go up to 100,000, 10,000 ohms. So stick to 1,000 for now in this example. So here are two ways you can do. You can find the voltage and current. You'll have to do both. First is the experimental way. So once you complete a circuit like this, take your voltmeter, multimeter, and measure all the voltages and currents across the resistor or in its sections. Okay, by using these voltmeter and ammeter, you are doing the experimental way, and you can verify your junction rule and the loop rule based on the experimental data. And the next is the calculation. So once you set this circuit here, once you build it, uh, take these R1 values and your potential values. Okay, use the values uh, as it asks you here. So it asks you to set the EMF values in the question. Okay, set as these here, and once you set these, write your Kirchoff's laws or Kirchoff's equations based on Kirchoff's laws. Okay, write these three equations that we learned earlier, and I want you to show your calculation here, all the mathematical calculation, solving three equations and find the values of current here and compare these your calculated values with the experimental values here at the end, and based on that, write down some conclusion here. Here are some extra questions uh, which you can use, the current from table 1 and circuit 1. So here you can use this current here, the experimental currents, okay, and verify the Kirchhoff's current law, which is saying that I1 plus I2 is equal to I3, or whichever way. We're looking at this junction here, sum of incoming currents I1 and I2 is equal to I3. So measure current here, here, and here, and see if this first law is verified. Similarly, take any loop and prove that the loop rule is correct, or the conservation of energy, or the sum of potential change across any loop, the loop 1, loop 2, or even the outer loop you can take, and that if that potential change is equal to 0 or not, verify it here. Okay, and finally, write down some of the conclusions that you found you saw from the Ohm's law and the Kirchhoff's law. So with that, you should have all the tools to work on this lab. Um, let's start the simulation and let's start today's lab.